will help prepare for today's lab, but that won't be on the exam.
Will you be reviewing it all?
Yeah, like I said, we'll spend part of the lecture on chemical equilibrium, the other part reviewing for the lab, for the exam now. I hope some of you have been attending the SI sessions with Alex because he's been reviewing questions from previous exams. He told me that he spent some time during the past week or so reviewing questions from last year's exam 1. Yeah, so quizzes from past semester are posted online.
So what will be covered on the exam?
All material through reaction rates. So that reminds me, let me review the chapters we've covered so far. Okay, so all the way back in January, we started by reviewing structure and bonding. And we applied our structure and bonding to chapter 11 on organic compounds. So when we looked at organic compounds, we spent time classifying organic compounds. And how are organic compounds classified? By, okay, maybe I'll spend a minute or two finding how organic compounds are classified on one of these slides here. Let's see. So they're classified by functional groups. So here are the functional groups that we looked at earlier this semester. And then we looked at some organic reactions. So for example, based on some of these functional groups, we know that an alcohol reacts with an acid to produce an ester. So you did that in lab 1. And we also know that an alcohol can be oxidized to an alcohol can be oxidized to what functional group? Yeah, so an alcohol can be oxidized to an aldehyde or an acid if it's a primary alcohol. For a secondary alcohol can be oxidized to a ketone. And can tertiary alcohols be oxidized? And if so, what can they be oxidized to? Tertiary alcohols can't be oxidized. Okay. So we start with the organic chemistry, and then we did some of these things. We talked a little about naming. I want to ask you how to name compounds in chapter 11. This is what we did in lab 1. Oh, we talked a little about resonance structures. Note that resonance structures are used because in Lewis structures, it shows localized electrons only. So with resonance structures, that means that electrons are shared or delocalized between 3 or more atoms in a molecule. Now we have to have some experimental evidence to determine whether resonance structures need to be drawn. Let's see, we talked about odors and smells, we talked about some molecular modeling. Okay, so we also talked about isomers. So note that isomers have the same chemical formula but different connectivity. Those are structural isomers. We also talked about stereoisomers. Stereoisomers have a different orientation in space. And we looked at, for example, the cis and trans isomers. And we've looked at very briefly enantiomers. I won't ask any questions on enantiomers on the exam. So here's some reactions that we looked at: alcohol oxidation, these condensation reactions. So one condensation reaction we looked at is the reaction of an alpha to make an ester. Also, there's the reaction between an acid and an amine to make an amide. Okay, so look at those two reactions. We looked briefly at plastics. There's two types of plastics: addition polymers and condensation polymers. So we looked briefly at those two types. And so that was from the quiz. We looked at some biomolecules and how biomolecules are classified. We looked at protein folding and protein shape and the primary, secondary, tertiary, and quaternary structures, and what chemical force is responsible for each type of structure. Okay, so look at more of those. I will not ask any questions on bonding theories. Then we looked at solutions. Now solutions is actually before we go on, so chapter 11 is on organic compounds, and then chapter 20, let's see here, chapter 20, chapter 22 is on polymers. So we looked at some sections in chapter 22. For the solutions chapter, that's chapter 13. So we looked at the solution process. So for Chem1B, if you want to get full credit for a question as to why one substance is soluble in another, you have to say more than this like dissolved like fluid. Okay, so what do you need to say if you want to get full credit for in Chem1B for the solubility of one substance in another?
There's an molecular
yeah, so you have to look at lattice energy versus, and what type of solution does that refer to, those energies? Yeah, ionic solutions. What about molecular solutions? What's an ion force? Ion force, is that what you said? I am. Oh, yeah, intermolecular forces, okay. Okay, yes, we looked at ionic and molecular solutions. That's in chapter 13. Now, in lab, you did a liquid-liquid extraction when you made that banana or wintergreen smelling ester. Okay, so how does an extraction work? So you have two substances. Actually, let's say you have two solvents. The substance, one substance is soluble in solvent 1. Then you add solvent 2, in which solvent 2 is immiscible in solvent 1. So how does this extraction process work? It has to be polarity, yeah, but that doesn't answer the question. So, what was the reason for doing an extraction when you did this in lab?
to remove the extraction.
Yeah, so it's the purified substance, but also using it to separate one substance from another. So when you did this in lab, for example, you made that banana ester. So let's say that banana ester, remember if it was the top layer or bottom layer? Bottom. That was the bottom layer. So what were you trying to remove from that banana ester?
Excess water.
Excess water and anything else?
The impurities.
Yeah, what were the impurities?
Unreacted things.
Yes, unreacted things. So you just can't say unreacted things. What does that say? What were the reactants when you made the ester? Huh? when you made the banana ester, did you use ethanol? No, you use salicylic. The banana ester is isoamyl alcohol and acetic acid. For wintergreen, that was salicylic acid and methanol. So you're trying to remove from the banana ester any excess water and any unreacted acid or alcohol. So what did you add to the banana ester to remove those substances?
Water.
Yeah, water. So what is the water doing? Another, how is the water extracting those substances from the ester?
Those substances are more soluble in water.
Yeah, so those substances like essentially are more soluble in water than they are in the ester. So by adding the water, since those substances are more soluble in water, it's going to extract those substances from the ester layer to the water layer. Okay, so that's a separation technique that we used. Now note also you did a solid liquid extraction when you made coffee and when you did that caffeine extraction. So how does a solid liquid extraction work? So, I mean, you guys don't think about this when you make your coffee or drink your cup of coffee every morning? You don't think of, oh, my coffee isn't strong enough because I didn't extract enough caffeine or coffee flavor from my coffee this morning because the hot water didn't stay in contact with the coffee beans as long as it should have. So you guys don't think about that when you make your coffee? You're just thinking about how much sugar and cream to put in your coffee, and because it's not tasting as, you don't like your coffee straight. Yeah, so anyway, so how does that solid liquid extraction work? So what are you trying to extract from the solid coffee? And what are you using to extract it? Yes, you're using water, so can you use pretty much the same explanation for a solid liquid extraction as for a liquid extraction? Yeah, pretty much. So you can say that what's more soluble in water than in the solid coffee beans? If you're explaining a solid liquid extraction to make coffee.
Caffeine and the
caffeine.
stuff that makes it brown.
Yeah, all the other stuff in the coffee is more soluble in water than they are in the coffee beans. Okay, so we talked about that. Then we talked about, let's see, different types of solutions. So for example, saturated solutions. And we talked about solubility. So we know that solids are more soluble than hot solvents. In a hot solvent, gases are less soluble than a hot solvent. We look at these colligative properties. So these colligative properties are also described in chapter 13. Now, before we go on, I just want to refer you to table 13.2 on page 450. It shows the boiling point elevation and freezing point depression constants of several common liquids. So you may want to have that page marked just in case you have to look up, say, KF or KB for one of those solvents in case you're asked a question on the exam as to, for example, calculate the freezing point of this solution or boiling point of that solution. Dylan? Page 450, table 13.2. Okay, now, just as an aside, I noticed that many of you bring your books to class every lecture, which is good. And then I've also noticed that the students who don't bring their book to class forget to bring their textbook to the exam. And then they ask me, can I borrow your textbook? And guess what my answer is? Yes. No. Because it is your responsibility to bring the materials you need for the textbook. Okay, here's all I got to say about that. Okay, so we talked about those colligative properties, how to apply those colligative properties. Yes, we looked at quite a few of the applications of these colligative properties. Oh, then speaking of this, two groups sent me their data for this part of Lab 2. So I'm still trying to compile the rest of the data because what we're trying to do is compare how these three methods work to determine the pressure of CO2 in soda. So far I only have two. Then one set of data didn't provide enough data to determine whether it was number 1, number 2, or number 3. Okay, so I've got to ask the groups that gave me that data what's going on with that data so we can finally get done with Lab 2. Okay, so you guys made ice cream. See, I'm guessing you guys remember the ice cream lab because you got to eat your lab. That's what I'm concerned about the other labs that you may be tested on the exam because you didn't get to eat those things. Okay, then this is the section of reaction rates. So reaction rates is the topic of chapter 14. So chapter 14, we looked at